All right. If you guys remember when we started talking about systematic ways to solve a circuit, we said there are two different ways of like doing it. The first way was like nodal analysis, which was based off of KCL at each node. And then we said we can write KCL at each node, and then we're going to solve for like node voltages. What we ended up getting was a bunch of like linear equations. We could put it into a matrix and solve for node voltages, and therefore we could solve for whatever we wanted in the circuit. Another method, another systematic way to solve a circuit is called mesh or loop analysis, which you can think of it as a dual of like nodal analysis. In the sense that like over there, we were just writing KCLs. Over here, we're just going to write KVLs. Over there, we were just writing KCLs at each node. Over here, we're going to write KVL for each loop. Right? So let's talk about it. Let's just see like how we can apply it. So just like nodal analysis, mesh analysis or loop analysis is again a linear method. What it means is that if we write down all the KVLs, since KVLs are in general, linear operators, so we're going to end up getting like a bunch of like linear equations, and therefore we can put it into a matrix and solve for, in this case, loop currents, right? So mesh analysis is a linear method, just like nodal analysis. But what does it say? Let's just say we're given a circuit. Assume we're given a circuit. Here's the recipe we should follow. The first step is to identify the loops and assign a current to those loops. So first step, identify loops and assign a current to the loop. Right? Second step, we got to write KVL for every single loop that we have. So step 2, write a KVL for each loop. KVL can be a little tricky. Why? Let's just assume you have a resistor, and that resistor is only in one loop. What is voltage across it? Well, we know Ohm's law holds. So voltage across it would be R times current. So no issue whatsoever. How about this resistor is shared between like two loops? What can we do? The idea is the same. Ohm's law still holds. The only thing that changes is that we're going to have to like use the net current that's going through that resistor. What do I mean by that? Case 1 is when there is a resistor, and that's not shared between like loops. It's only in one loop. Voltage across it, let's just call it V. Current through it, I. We know V equals R. Case B, let's just say I have this resistor. Let's just say this is positive, this is negative. But this resistor is between two loops. Let's just call this one I1, this one I2. Basically, I1 and I2 are going into two different directions. If I go from here to here, what is voltage across R? Well, obviously, I still have Ohm's law, right? So it's R times whatever current that's going through this. But what is the current that's going through? Well, I1 is going this direction. I2 is going the opposite direction. So what is the total current that's going through this? One of them is going one direction, the other one's going another direction. What is the total? It should be the difference. So V here would be R times I1 minus I2. Right? So again, we still have Ohm's law, but this time this current through here, this, if I call it I, this is I. Right? Case 3 is that, again, I have this resistor. This time, this is I1, and this is I2. Again, I have Ohm's law, right? So if I go this direction, what is current through this? Well, I have I1 go in this direction, I2 go in the same direction. So what is the total current? What is it? It's just a summation of that, right? So if I call this I, V equals R times I1 plus I2, and obviously this is my current, right? And the third step is to just solve for unknowns. Okay. Recipe is like very simple. We're just going to write KVLs. Okay. So let's just do an example to see like how we can actually apply this, right? Example. Let's just say I am given this circuit. I have a voltage source with value V1, 1K resistance here, another 1K resistance here, a 1K resistance here, and V2. Right? Well, let's just say V1 and V2 are given. By that, I mean, like, we know the values, 5, 6, whatever. That's given to us. We're not trying to solve it. Right? So let's apply this method. The first step is to tell me identify the loops and assign a current to each. Right? Do you agree this guy over here is one loop? So let's just have it and call it I1. Do you agree this is also another loop? Let's just call it I2. Do I have any other loop? I do. I have like this big loop over here, but I don't really care about it because I already covered it by I1 and I2. Right? What is the second step? Let's just write a KVL for every single loop that I have. So let's just write a KVL for loop 1. Let's start from here. I'm going clockwise here. Okay, writing the KVL. Does it matter like what direction I choose here? No. I chose to be clockwise. You can be, counterclockwise. You can assume one of them is clockwise, the other one is counterclockwise. But as soon as you decide, you got to stick to that direction. You cannot change it in the middle. For this problem, I chose to be clockwise, right? So I'm going this direction. What do I have? I have negative V1. What is voltage across this 1K? This is the easy one. This is the one that's in one loop. So what is voltage across it? That's 1K times current through it. What is current through it? I1. How about this guy? What is voltage across this? Voltage across this is again the value of the resistance, 1K, times current through it. But what is current through it? Remember, I'm going this direction. I1 is going downwards. I2 is going upwards. So if I go this direction, what is the total current that I have? What is it? That's I1 minus I2, right? Again, remember, I1 is going down, I2 is going up. They're opposite directions. So it's I1 minus I2. I got nothing else, so I close the loop. That should be simple. I can simplify this. I have one I1 here, one I1 here, so I have two I1 minus one I2. I take this one to the other side. I have right. Call this equation. Right? I just wrote the KVL. Let's move on to loop 2 and write the KVL for loop 2. Let's start here. What is voltage across this 1K up here? Again, that's a simple one. It's not shared between two loops. It's only in one loop. What is voltage across it? That's the value of the resistance times current through it. What is current through it? I2 plus V2. Now I have this 1K that's shared. This time I'm going this direction. I2 is going upwards. I1 is going downwards. What is the voltage across this? That's the value of the resistance times current through, which is I2 minus I1. And I close the loop, and that's it. Right? Again, I can simplify this. I have 1K I2 and 1K I2 here, and negative I1 over here. So I have 1K I1 with negative sign plus 2K I2. That equals negative V2. And that would be my second equation. Right? As you can see, both these equations are linear. To solve for I1 and I2, I can put them into a matrix. So let's do that. So I have I1 and I2. This is my unknown matrix. This is my unknown vector. I have my coefficient matrix. And that should be my constant, basically, vector. The first equation tells me 2K I1, so I put a 2 over here, negative 1 I2, negative 1 I2. That should be V1. So this is 1. Second equation tells me negative I1, so negative 1, plus 2K I2. That should be minus V2. Right? Again, this is my matrix A. This is my unknown X. This is B. I can solve for X, which is I1 and I2, which is A inverse. Right? So I can get my out. Just like nodal analysis, if I have loop currents I1 and I2, I know everything in this circuit. Right? Let's just say voltage across this guy is V out. Right? What is V out? What is V out? We solve for I1 and I2. We know exactly what it is. What is V out? Again, we have Ohm's law. So I have 1K. Given this polarity, what is it? What is the current through it? Again, I1 minus I2 times I1 minus I2. We already computed these two, so we know V out. What if I told you V out had like opposite polarity? Down here was positive, over here was negative. The current would be negative of this, right? Would be I2 minus I1. Because I2 is going upward, I1 is opposing that, but the whole current should go upward. Right? But if we had like nodal analysis, even though we were writing like KCLs, what we solved for was node voltages. Over here, we can say the same thing. Even though we're writing KVLs, but what we're solving for these loop currents, right? So let's make that a quick remark. When doing mesh or loop analysis, even though we're writing KVLs, we're solving for loop currents. And remember, as soon as I know like loop currents, I know everything in the circuit, right? I can compute everything. Right? Is that clear what's going on here? You guys with me so far? Everything good? Does that make sense? Yes? Yep. All right. Let's make it a little more interesting. Let's do another example. Let's just say we're given this circuit. Example. Let's just say I have a 2K resistance here. I have a 12 volts. I have a 2 milliamps current source, followed by 2K resistance, a 1K resistance, and a current source with value 4. Oh, let's just say the question's asking us, what are loop currents? Right? What do we do? What is the first step? What is it? Identify the loops. So I'm going to say, this is I1, this is I2, and this is I2. Do I have any loop that I haven't covered? Covered all the loops, right? There is no loop that's not labeled, right? Again, I chose the direction to be clockwise. I could have just chosen one of them to be clockwise, the other one counterclockwise. Didn't matter, right? Yes, what was your question? I could, but I don't have to because I already like named all the loops. The outer loop would be a combination of like those other two loops, right? What is the next step? I got to write a KVL. Can I write a KVL here for loop 1? No, I cannot. Why? Because I don't know voltage across this current source, right? I know current through it, but I don't know voltage across it. So let's move on to the second loop over here. Can I write a KVL for this loop? Still no, because I don't know voltage across this guy. With the exact same reason, I cannot write a KVL for this third loop, because I don't know voltage across this guy. What was our solution when we're dealing with like nodal analysis and voltage sources? We had to find a way to get around them, right? We have to do the exact same thing over here. But what I'm claiming is that if I look at I2, I know exactly what I2 is. What is the value of I2? What is it? It's -4. Because what it tells me is that I have a current source here with the value 4 milliamps going up, but the direction of I2 is the opposite of that. So that should be -4. So just like nodal analysis, that voltage sources were either super easy when they were between a node and a reference. Current sources for mesh analysis are very easy if the current source is in one loop. In nodal analysis, voltage sources were problematic when they were between two nodes that neither of the nodes were reference. Over here, current sources are problematic if they're shared between two loops. Basically, that 2 milliamps, since it's shared between two loops, it's problematic. I don't know exactly what's going on. So let me make that quick note. Doing mesh analysis, current sources are either one, super easy, and that's when they're only in one loop, or they're problematic, and that's when they're shared between two loops. In nodal analysis, we said it was problematic. Then the idea was to get around it and form a supernode. Over here, we're going to get around it and basically go around here. And we call it a super loop. Very innovative, very creative, right? So the solution here is a super loop. If I write the KVL for the super loop, then I don't have the issue with that current source in the middle, right? So let's do that. So let's write the KVL for the super loop. What do I have? I have minus 12 plus voltage across this guy. What is voltage across this guy? That is 2K times current through it. What is current through it? I3. I'm going to go here plus 1K times current through it. What is current through this guy? Remember, the direction of the supernode is this. I3 is the same direction. I2 is opposing them. It's the opposite direction. So what is current through it? It's I3 minus I2. Right? Plus, I'm going to go here. I have R, which is 2K, times current through it. What is current through this guy? Again, I1 is going down. I2 is the opposite direction. So what is current through this guy? I1 minus I2. Right? Remember, I1 is going down, which is the same direction as my super loop. I2 is the opposite direction of my super loop. So it's I1 minus I2. And I close the loop. That should be seen. Right? Just like nodal analysis, when we form that big, giant supernode, we're losing information. By combining these two loops, we're still using information. So we have to utilize that information that we have. What is that information, though? The information here tells me, if I look at this source tells me I1 is going this direction, I3 is going the opposite direction, the net current is this direction. What does it tell me? It tells me I1 minus I3 must be 2 milliamps. Right? Does that tell me that? I1 is going this direction. I3 is going backward. But the net current is going forward. Right? So information provided by superloop tells me I1 minus I3 must be 2. Right? So far, you with me? Does that make sense? What's going on? Right? Again, just remember, it's exactly like node analysis. Over there, we had like a giant node, we call it a super node. Over here, we have like a giant loop, we call it like a super loop, right? And since we're combining loops here, we got to like utilize the information that each loop was given us. And that's basically this guy. I'm claiming like I2 is just variance, right? That's the easy part of the current source. So looking at loop 2, we know I2 is -4 moles. Look what I got. I have 3 equations, 3 unknowns, right? I can solve for I1, I2, and I3, right? So we have 3 equations, 3 unknowns. We can solve for I1, I2, but as soon as I have I1, I2, and I3, I have everything in this circuit. Whatever question I ask you, you know exactly how to answer. Let's answer a few questions. Let's just say we define this guy to be the out. I know I1, I2, and I3, right? What is the out? Exactly. I have Ohm's law. I just need to like multiply the value of the resistance by the net current passing through. Given the polarity of the out, I know the out would be 2K times current through this guy, which is I1 minus I2. Right? What if I call voltage across this one the out one? What is the out one? What is voltage across this one? Any ideas how I can find the out one? What I'm claiming is that I'm going to write a KVL for that loop 1. And that would give me the out one. So let's see how. So we're going to write a KVL. So to get the out one, write a KVL for loop 1. If I write a KVL for this loop, I have -12. I have plus the out one, plus voltage across here, right? Which is 2K times I1 minus I2. And that should be 0. Right? I know I1 and I2. Doesn't matter if I already computed this guy. This is the out. Right? So I can compute it. Right? What if I told you find this voltage? The out. What is that? How can I do this? Well, all I need to do is to just write a KVL for this, right? I'm going to know exactly what this voltage is. So KVL for loop 2 to get the out. How do we write it? Let's go here. What do I have? I have 1K times, what is current through this guy? I2 is going this direction. I3 is going backwards. What is current through it? That's I2 minus I3. Plus the out 2. What is voltage across this? That's 2K times I2 is going up. I1 is going down. What is current through it? That's I2 minus I1. And that should be easier. I know everything here. I can compute the out. What I would like for you to pay attention to is this term right here. Do you agree this is negative V out? Remember like what V out was? 2K I1 minus I2. I'm claiming this guy right here is negative V out. I just need to like factor out a negative. So what is the point here? The point here is that as long as I stick to the directions that are already assigned, math will work out. So if I know this is V out with this direction, V out is 2K times I1 minus I2. But if I go this direction, this is going to be negative V out. But since I'm sticking to the direction that I had, this negative V out is indicated over here by this negative sign down here. Right? So we don't have to worry about anything. As long as we have the correct assignment, meaning sticking to the assignment that we had, everything will work out. We don't have to worry about anything. Any question on this? Any question on this? Does that make sense what we're trying to do? Yes? So again, we don't have to worry about like the polarity. It works out if we have the directions and stick to the directions of. Okay? And given this circuit, I can always solve for like loop currents. And as long as I know the loop currents, I know everything in the circuit. Right? I can compute whatever. Right? Sometimes it's very straightforward. I can just write Ohm's law. Sometimes I have to write a KVL, or sometimes I have to write a KCL. Right? So let me quickly compare these two methods that we learned. So comparison between nodal analysis and mesh. Basically, there is a duality between these two methods. I'm going to explain what I mean by duality in a second. So let's just have everything about like nodal analysis here. And everything about mesh or loop analysis over here. The first thing we know about like nodal analysis is that we have to write KCL at every single node. Right? That was our method. So KCL at each node. How about the mesh analysis? What do? We wrote KVL for every loop. KVL for each loop. Right? So if I basically replace current by voltage, node by loop, if there is a duality, everything else should follow. right? Let's see if it actually is the same. For nodal analysis, we're solving for node voltages. If this mesh analysis is the dual of this, we have to replace node by loop, voltage by current. And that's exactly what it is. We're solving for loop currents. In nodal analysis, voltage sources were either super easy or problematic. So voltage sources are either easy or problematic. Over here, current sources are either easy or problematic. Our solution for nodal analysis was supernode. Our solution for mesh analysis is superloop. So basically, if I change the role of current with voltage node by loop, I can go from like one to another. And in this sense, they're actually dual, right? There is one big difference here. If you recall, I said nodal analysis is the most general way that you can solve any circuit. So that can be applied to any circuit that you have. However, I cannot say the same thing about mesh analysis. Mesh analysis cannot be applied to non-planar circuits. And what do I mean by non-planar? Non-planar basically means I cannot just draw the circuit on a piece of paper without removing my pen. It means like there are a lot of lacrosses going on a piece of paper, which if I actually write it on like 3D, if I draw it on a 3D, there is no cross. Right? But I still can apply nodal analysis. So nodal analysis can be applied to any circuit. This method cannot be applied to non-planar circuits. You have one example like this in your homework. But you cannot use mesh analysis. You got to go back and do nodal analysis. Right? But keep that in mind. Nodal analysis is the most general way of solving any circuit. Right? Mesh analysis is fantastic only if the circuit is planar. Right? Any question about this? Any question about the comparison? Nope. Yes. Can you speak up, please? Planar? Yeah. Like I said, planar means like if I want to draw the circuit, I can draw it on a piece of paper without removing my pen. Right? So there is no cross going on. So I have to like remove my pen and redraw it. I can just draw it just like. Okay. All right. Let's do one more example. Let's just say I'm given this circuit. 5 volts, 5K resistance, a 12K resistance here, 6 milliamps over here, a 6K resistor, a 3K resistance, and a 6 volts source. All right. Let's just say we're interested in VI. What method do you want me to use? Not a trick question. You can just tell me like whichever method you want me to solve this. Which one? Nodal? Let's do nodal. What is the first step? Just choose a reference. I'm going to choose this one down here as my reference. So what it means is that voltage here is the same as voltage here, is the same as voltage here, and they're all zero. Right? Do you agree this one up here is a node? So let's just call it V1. Do you agree this one over here is another node? Yes? No? Is this one a new node? It is, because there's a potential difference here. So let's just call it V2. How about this guy over here? Is that a new node? It is. That's V3. How about this guy? Is that a new node? It is, because there's a potential difference between these 2 points. There's a voltage drop, right? So that's V4. How about this guy? Is that a new node? It is, because if I look at V1, it is different than V1 because there's a voltage drop. So let's just call it V5. Right? Now I have to write KCL for every single one of them. Right? What I'm claiming is that, you see, that's my observation. I don't need V5. Why? Why do we not need V5?
The voltage across it.
We don't. We don't know the voltage across the 6 milliamps current source. We don't. What is it? Look at that branch. I know exactly what current through it is. Right? If I look at this branch, I know exactly what current through this branch is. What is that current? That's 6 milliamps. So there's no point writing like KCL, or basically like knowing voltage across it. So our observation here, observations, we do not need V5 since we already know current through that branch. What else can be observed? Do you agree V2 is 5 volts? Right? That's the voltage source that's between a node and the reference. That's the easy one. What else can be observed? I claim I don't need V4 either, because I know what it is. What is V4? It's negative 6 volts. Again, that's the easy one. It's between one node and the ground. Right? So V4 minus 0, it's minus 6 volts. So the second observation is that V2 is 5 volts. Third observation is V4 is negative 6 volts. Right? Let's just write a KCL at node 1. So the KCL at node 1. I'm going to assume everything is going up. Right? What do I have? What is current through here? It's V1 minus V2 divided by 5K. This one is also going out, so it's V1 minus V3 divided by 6K. That should be the same as the current that's going in, which is 6. But I already know V2. I can plug it in here. That's 5 volts. Right? Let's write a KCL at node 3. I already decided on direction here. So let's assume this is going out as well. So whatever current that's going in should be the same as whatever current that's going out. I have V1 minus V3 divided by 6K. That should be the same as V3 minus V4 divided by 3. But we already know V4 is minus 6. I have 2 equations, 2 unknown. I can solve for V1 and V2. Right? What is V out? What is V out? V out is V1 minus V2. Right? So it's V1 minus V2. Right? Please bear with me a couple more minutes so I can actually solve this using mesh analysis quickly. So let's just say I'm given the circuit. So 5K, so 12K, 6 milliamps, 6K, 3K, negative plus. Again, the idea is that I have to assign currents here. Let's just say this is I1. I'm going to make it this time a little more interesting. I'm going to say I2 is going backwards. Right? It's up to me. Can I write a KVL at this node? No, because I don't know voltage across this current source. Right? So the idea here is that I have to do the super loop. So I'm going to say this over here is my super loop. Right? So KVL for super loop. What does it tell me? It tells me I have minus 5 plus 5 times I1 plus 6K times current through this. What is current through this? It's negative I2 because I2 is going this direction. My loop direction is the opposite of that. So it's negative I2. Plus 3K times current through this. What is current through this? It is still like negative I2, right? Because my loop direction is clockwise, but I2 that I consider is the opposite of that. So that would be negative I2 minus 6. That is 0. Right? I still have not utilized the information that this super loop gives me. Info from super loop. What does it tell me? I1 is going downwards. I2 is going downwards, but the net current is going upward. What does that tell me? It tells me I1 plus I2 should be negative 6. Right? I have 2 equations, 2 unknowns. I can solve for I1 and I2. If I know I1 and I2, again, remember this is V out. What is V out? It's 5 games times current through it. What is current through it? Is it I1 or minus I1? It's negative I1. Right? And that's it. So what we're going to be doing next lecture, we're going to talk about like superposition. And then afterwards, we're going to start talking about optics.